Hey everybody, this is Mr. Bortnick, continuing on in our AP Calculus AB content. We are in Unit 1, Limits and Continuity, and we're continuing on in topic 1.4, which is estimating limit values from tables. So please title today's notes, topic 1.4, estimating limit values from tables. Enjoy the notes. All right, for today's lesson, section 1.4, finding limits from tables, calculator will be required for part of this lesson. And so if you've got your graphing calculator with you, that's great, use that. Otherwise, you're going to want to pull up the links to the online graphing calculator, which I shared in our syllabus. We're going to be going through some specific calculator tricks that are going to be really useful for you as you go through this, and so you're going to want to follow along. Great, we're going to jump right into the worksheet. So on this worksheet, if we have the graph, it is easy to see the value of the limit as x approaches 3 of f of x. Again, visually, we can tell that by looking at x equals 3. We're looking at that actual point, and since there's no left or right given, no exponent with that negative or plus sign, we know that we're talking about coming from the left and from the right. And so if we follow from the left and from the right, we see that that limit visually, graphically, is 4. And so that limit is going to be 4, and that is a graphical interpretation of finding that limit. Calculus, and specifically the AP Calculus exam, talks about the connection between different representations of math. So graphical is one way, a table, which we're going to be talking about, is a different way, and then algebraically is a third way, which we're going to be talking about, I think, lesson 1.6 when we get to it. So similarly to the graphical way, we could take a look at a table of values. Notice that for this, we're still trying to find the limit as x approaches 3 of f of x. And so we would notice that if these x values are in order, that 3 would be right here in between 2.99 and 3.01. And if we were to actually make this table, noticing in our graph, this graph has an open circle at 3, 4, I'd imagine that if we actually found this value right here or had a function for it, it would say that this is undefined. Or maybe on your calculator it might pop up as an error because there's no actual value at that particular point. So the question then is, how could we use a table of values to approximate the limit? In that case, we're going to look at the y values coming from both the left and the right side. And so here, if we take a look at our table, this is our table of values, which are also in the graph, but here are my values from the left. We notice that as the x values get closer to 3, they get really, really close, like 2.99, or we can get even closer and go like 2.99999. The closer we get to 3, we notice that these y values are getting closer to what looks like 4 from this side. Similarly, if we take a look at the right side, we notice that as it gets closer to 3, that the y values are also getting closer to 4. So we can estimate from this table that the limit as x approaches 3 of f of x is also equal to 4. This is the same as what we're seeing in the graph. Now, I'm being very specific in saying that this is only an estimate of the limit because we don't actually know, for sure without the function itself what's happening between, say, like 2.99 and 3, right? It could be doing all sorts of things. But looking at the values that we're given and without being given the actual function itself, this is the best we can do, is to try to make an estimate of what that limit is. And so that is how we would do this with a table. Let's move on to number 1. Number 1 says, according to the table, what is the value of the limit as x approaches negative 4 of f of x? In this case, we notice that negative 4 would be here. It would be between negative 4.001 and negative 3.999. And so since they're not asking from the left or from the right, we need to consider both of those. So as we come from the left, as those x values get closer to negative 4, to me it looks like those y values are getting closer to a particular number, maybe like 2.5. And if we come from the right, we see as it gets closer to negative 4 that those y values also appear to be getting closer to 2.5. So because of that, my overall limit statement is going to be the limit as x approaches -4 of f of x is equal to 2.5. And again, this is just an estimate using this table. Without the function itself, we can't be 100% certain, but that's definitely what the table is telling us here. All right, next for number 2, we've got the if f of x is equal to this equation, x cubed minus 4x squared minus 7x plus 10, all divided by x plus 2. Create your own table of values to help you evaluate the limit as x approaches -2 of f of x. We're going to pause now and switch over to our calculator because I want to show you a good calculator trick. All right, so I've got my digital graphing calculator here. You'll notice that it's a TID4 plus CE. What I'm going over is a calculator trick for both TID3 and TID4. If you've got a different graphing calculator, it is entirely possible that your calculator can do those tricks, but you might need to look up how to do it. I'd say a majority of our students have these types of calculators, which is why I'm going to be using those for our demonstrations. So for this problem number 2, I want to remind you, it sort of asks us to create our own table of values to evaluate a specific limit. And so what I did first with my calculator is I typed in the equation into y1. And so I've got x cubed minus 4x squared minus 7x plus 10 in parentheses. And that is all being divided by x plus 2 in parentheses. You can use that special feature on your calculator if you've got a newer one where it turns it into a fraction. That would work as well. But definitely, if you're writing it out without that, you want to put parentheses around the numerator and parentheses around the denominator. Now it said make a table. And for me, I'm thinking about if they want the limit as x approaches -2 for this particular problem, I'm going to want values of x that are very, very, very close to -2. Now, like being at like -1 or -3 is actually not close enough. And if I hit second and go to my table, so second graph would bring up my table, we notice that our table is normally set up with just like integers here, right? These are specific integers that we've got. And I'd say we see an error at -2, which if we take a look at the equation itself, if you plug -2 into the denominator, -2 plus 2 would give us 0. So that would be causing the equation to divide by 0. So it spits out an error as the output for that. So the question then is like, how do I get this to make a table that's like actually useful for me? In this case, what we can do is by using a feature that's called table set. And so what I'm going to do is I'm going to hit second and window to bring up that table set menu. And you'll notice that this is saying, hey, set up your table. For me, the table is starting at -6. This is the amount that it's going to go up by each time. So it's going up by 1, which is why we see it is going -5, -4, -3, -2. And then these are both currently set to auto. What I'm going to do to change this up is I'm going to actually go to my independent variable, and I'm going to have it ask me instead of actually doing auto. And what you'll notice now is if I hit second and go to my table again, now it is not typing, it is not showing me actual values here. I can actually type in any values that I want. So in this case, because this is asking the limit as x approaches -2, maybe I'll do something like a -2.1. I want to find out what that value is. Oh, I can actually type that value in, and it's going to show me what the y value is. If I get even closer, if I do like -2.01, whoops, if I do -2.01, we would get a value that looks like that. If I get even closer, like -2.0001, that looks like that's getting 21.001. So these are all values that are less than -2. And this, it just rounded the decimals away, even though I typed in that 0.00001. I also want to make sure I have some values that are greater than it as well. So I'm going to try like -1.99999. That's greater than -2. I'm going to try like -1.9. And we notice in this case that the values, as it gets closer to that -2, to me look like those y values are getting closer to 21. But also something to notice here is this is really nice because we can get whatever values of x we want. I can actually move up on these and rewrite. If I wanted, say, like -5, I could do that there. Whoops, go to, that's a minus sign. I need to make sure that's a negative. So if I want like -5, it could tell me that. If I wanted 100, it could tell me that. That's a really fancy way to get your calculator to tell you function values without needing to be on the home screen and needing to type like the whole equation in each time. It's a really short way if you've got the equation written in y equals already. But what my problem here is you'll notice that even for this one right here at -2, is we know that there were some decimal places here and the calculator rounded it. The reason why the calculator rounded it here is because we noticed that the box has a certain width for this table. And the calculator says if it's too wide here, we're just going to round it. And so that makes it a little bit tough to see exactly what's going on sometime. So I'm going to show you a second way that we can do this as well. So let's go home. I'm going to hit second and quit to go back to that home screen. And we're going to confirm, yeah, the y equals, the equation is still in y equals. So I'm going to clear out this bottom, this clear press history, so you can see what we're going to do next. Now, what we're going to do is essentially function notation on your calculator, right? If we were to say like f of 3, we know that if the equation that's right here is f of 3 would be if we plugged in 3 in for each of those x's, and we would get whatever that output is. Your calculator can essentially do function notation if we tell it to. And so here's how we do it. We're going to hit the vars button, so for variables, and we're going to go to where it says yvars. So I'm going to move over to yvars, and then I'm going to hit function. So I'm going to hit enter, and then I'm going to have it call y1. y1 is whatever I have in the y1 equation up here. So this is my y1 equation. Hey, I've already got it here. And so y1 is going to be that equation. I'm going to do this just like function notation. So I'm going to move and I'm going to put parentheses. And let's say we want 100. What's this equation if we plug in 100? Close that. So what is this equation when the input is 100? Hey, it's 9,405. What is this equation if we do second, or actually if we do, yeah, I'll do vars again and just pull that up. So if we do y1 of 5, that's going to be this. Also a useful way is to pull up from the memory. So I'm just going to hit second and then mem. Actually, not second and mem. Second and then entry, second and then enter. And that pulls up the last thing, and I could just go over and edit what that particular value is. So similarly here, I want table values that are close to -2 for this particular problem. And the reason why I'm doing it this way is because it's going to show me more decimal places. And so I'm going to put in I'm going to put in -2.1, close those parentheses, and that tells me 22.01, and there's no decimals after that. If I hit second and entry, it's going to bring that up again. Let's try -2.01, close the parentheses. Well, that's going to be 21.1001. That's already more than they showed in the table that they made for us. Let's try this again. If we do second and entry, bring that up again. Well, let's add an extra 0 here and see what happens. To me, these look like these are getting really, really close to 21. And again, we're going to do the same thing going in the opposite direction. If I do this, but if I do it with like -1.9, that's 20.01. If we do -1.99, 20.9001. Let's do this one more time. -1.999. Close those parentheses. Hey, that is really, really close to 21 as well. So I'm thinking here that the limit is going to be 21. And we're going to jump back to our worksheets to fill in that table and find that actual value. But this is a nice little calculator trick to get those decimal places as well. All right, so back to our worksheet. We're being asked again to create our own table of values to evaluate the limit as x approaches -2 f of x. In this case, the question you should be asking yourself is, hey, what x values should I actually use for this? If I'm making my own table, well, it would make sense to have -2 here in the middle. And as we saw on our calculator, we saw that there was an error, and that is because this is undefined at that particular value. And again, we can see that because if we look at the equation, if I plug in x equals -2, in that denominator we're going to have a -2 plus 2, which is equal to 0. And we know that we cannot divide by 0. And so because of that, that is spitting out an undefined here, or on your calculator it's showing up as an error because of that. What I'm going to do next is I'm going to think about what values I want. I want some values that are very, very close to it from above and below. So I'm going to do -1.999 and -1.99 to get some values that are slightly above. And then I'm going to do -2.001 and -2.01. The values that you use closest to this are going to be most useful. I wouldn't want to pick numbers like -3 or -4 or -1 and 0. Those are too far away. So in general, when you're picking the values for the table, closer is always better when you're doing that. It's going to give you a better estimate of that limit. So closer is always better for those x values. And then when we set that up, when we used our calculator to find those actual values, we saw that at -2.01 that the output was, in this case, well, the output was 21.1001. So the question then is, how many decimal places do I actually need to write? And there's a rule for AP Calculus, and this is true for the AP exam. In this class, you should always use, so always, if you're rounding, so always round to 3 decimal places. We always round to 3 decimal places in AP Calculus. And this is a standard on the AP exam. We're going to need to do this all throughout the year so that we get used to it. They expect you to round to 3 decimal places, which actually means if you round to 1 or 2 decimal places, that your answer will be wrong. They require that you do it to 3 decimal places. So when I have a number here like 21.1001, I could round this one of 2 different ways. One way is called truncating, which essentially is cutting off all the numbers after the 3rd decimal place. So that would look like 21.100. Or we can round, which in this case would actually give us the same thing. 21.100 would give us the same value, because since that's a 1, that's not going to move that next number up as well. So those give us the same value, and so we're going to put that into our table like this. For -2.001, we had 21.01. And over here, we had 20.99 and 20.01. Always key when you're making a table or working with calculus, if you're rounding, it must be to 3 decimal places. Now, for our limit, we notice here, from the left, it looks like it's getting closer to 21. From the right, it looks like it's getting closer to 21. So overall, I'm going to say that my final answer for this is that the limit is 21. And that's nice. It'll be a little bit faster when you use your calculator and get used to finding those actual values. But I'm trying to really show the steps of filling out those particular tables. So again, this says there's several ways to find values of a function on a calculator. The 2 ways are table values, so it's not particularly accurate, but it is fast. And then the function notation way is more accurate because it shows more decimal places. So those are 2 ways, 2 little calculator tricks you can use in order to fill out those tables and hopefully speed this up. Now, number 3, let's wrap this last one up. The function f is continuous and increasing for x is greater than or equal to 1. The table gives values of f at selected values of x. Approximate the values of the limit as x approaches 2 of the cosine of f of x. All right, well, let's see what happens. We notice that this is a table of f of x. And as x approaches 2, 2 would be right here. So from the left, this to me looks like it's getting really close to 5. From the right, this looks like it's also getting close to 5. So to me, it looks like that f of x, if we're thinking about this, let me erase. If we're thinking about what this table is telling us, this looks like that the limit as x approaches 2 of just f of x is going to be equal to 5. Notice, though, that this graph is asking me the cosine of f of x. So I know that f of x is going to 5. I know this piece. And so then what we can then infer from this is that if f of x is going to 5, then that 5 is going to go in where that f of x is. So this should be equal to the limit. Oh, actually, this should be equal to, since we already did the limit, it's going to be equal to whatever cosine of 5 is going to be. And so in this case, I'm going to use my calculator to do that. And one more calculator tip for today is that in AP Calculus and on the AP Calculus exam, your calculator should always be in radian mode. And you can check that by hitting the mode button on your calculator. So there's a mode button. You should be able to check to see what mode your calculator is in. It's right next to the second button, radian mode. And so if we do that on our calculators, we should see that this is equal to 0.283662185 ... forever. And if we think about how we'd round this for AP Calculus, this should be equal to, if we truncate, that would be 0.283, or if we were to round, that would be 0.284. Either one of these would be acceptable answers for that problem. You could either truncate or round, and both of those would be fine. That's it for today's notes. Try out today's problems if you continue on for our practice problems. Do those, check your answers, and please come to class with any questions you've got. Thanks so much, and have a great day.